Here's our last topic in this particular short chapter. So far we've talked about Euler's method, which uses a differential equation to make an approximation, regular exponential growth, which we did last year in the differential equations chapter, restricted growth, which was Newton's law of heating and cooling. And we have one more type of growth left, and it's referred to as logistic growth. So I kind of summarized it a little bit in class the other day, but I want to go through it again. The idea if something grows logistically is that there is a cap. And when you think about, especially environmental science talks about this a lot, when you think about an amount of a particular species, you can only grow so much because you run out of resources. So we don't really have rabbits that grow exponentially. They grow exponentially to a point, but then it starts to slow down based on how much the environment can support. So when you look at logistic growth, instead of growing, you think exponential growth just like takes off. Instead of taking off like that, it starts off quickly and then it gets to a point where it starts to slow down. It's still increasing, but we would say it's increasing at a decreasing rate. So the graph looks like the picture that you're looking at. So we use the letter L, and I'm not sure who decided L. I think they used L for like limit to describe the carrying capacity of the environment. So how many people can we have in a certain environment, or how many rabbits? Or if we're looking at the spreading of like a rumor, how many total people are there out there that need to hear this rumor in order for, and then everybody to hear it? So that is your L value, and it's written as like a horizontal asymptote. So your graph, you'll notice, approaches it, but it can never surpass that because that is my max. As time goes to infinity, my function will eventually get to that limit or that carrying capacity. When you look at the actual graph, you'll notice that we actually have a point of inflection. Your graph switches from concave up, meaning it's increasing at an increasing rate, to concave down, meaning it's still increasing, but now at a decreasing rate. And that happens at half of your carrying capacity. So I have seen AP questions that are very straightforward. They don't want you to do a lot of work, simply wanting to know, when is that change? When is that time where it goes from increasing at an increasing rate to increasing at a decreasing rate? And it always will be half of your carrying capacity. So if you have a population, let's say you have a high school building that has 1,000 people in it, and you're trying to figure out, when will this rumor that's going through the high school be traveling at the fastest rate? And it will always be at that halfway point. So once you get to the point where 500 of the 1,000 kids know this rumor or have heard this rumor, that's the peak of transmission, basically. Same thing with a virus spreading, that you need to get half of the people exposed before you can say that the rate of increase starts to slow down, which doesn't necessarily bear well in our COVID situation. So when we have this written as an equation, we say that the rate of change of y, and y is your population. A lot of times we use p as well for population, is jointly proportional to y and the difference between L and y. So thinking in terms of a rumor, the rate of change depends not only on how many people have heard the rumor, but how many people haven't heard the rumor. So that's where we get this, not only the amount of the population, but the difference between the carrying capacity and the amount of the population. So in terms of equations, you'll see one of two equations written. You'll either see it written as this first one. Again, your y value is your population. So oftentimes we'll use a letter P instead of a y. So it's related to the population and the difference between your carrying capacity and the population. Sometimes it's also, they'll divide both things in the parentheses by L and write it as 1 minus y over L. The important piece for you as the student trying to answer these questions is you should be able to recognize an equation for logistic growth. You should be able to look at the equation and know what the carrying capacity is just by the way it's written. So again, your variable needs to show up 2 times. It needs to be both in front of the parentheses and in the parentheses, and that's a key idea with the equation. So I saw this question. This was on a PowerPoint I have somewhere. I might even be able to pull the PowerPoint. And it was talking about the number of moose that is living in a national park. And the idea is that the equation of the growth of the moose population is given here. So just because of that equation, the one thing you should realize is that the number in the denominator here is your carrying capacity. That is your L value. So that means your national park can only sustain 200 moose, and there is no plural of moose, just moose, over the course of time. And then the question says, well, if your initial moose population is 50, what is the limit of your moose population over time? And this question sounded like it was going to be a ton of work. Your limit is just 200 because that is your carrying capacity. So being able to look at this equation, recognizing what number here is the carrying capacity, that tells me that my moose population can only go over time to 200. Another question they could have asked that they didn't is they could have asked at what number of moose is the population growing most rapidly, and that would be at half the carrying capacity. So you could say that once you got to 100 moose in the park, that's your peak growth of your population. After that 100 mark, so anything from 100 to 200, we're still increasing our population, but it is definitely slowing down. So that is that point of inflection where you go from increasing at an increasing rate to increasing at a decreasing rate. When you're working with logistic growth models, and I'm going to mention this formula, these formulas multiple times, we have different equations we can use to actually solve this process. So the first one is how we actually solve a logistic growth model for the population. We take the L, which is your carrying capacity, and we divide it by 1 plus A e to the negative kt. Now, your A value has to be found as well. And your A value is by taking the second equation. You're going to take your carrying capacity minus your initial population and then divide by your initial population. And that's going to give you the constant A. And we put that constant into this equation. Now, these are kind of complicated equations. You will not be asked to memorize them. They will be written on the quiz. They will be written on the board. They will be written somewhere, probably multiple places, so that you can truly just use them. So you need to know kind of how to do the algebra, how to do the arithmetic, but you do not need to memorize this. And the reason I do that is I've never seen a question on an AP test where they make you memorize these formulas. The questions on the AP test tend to be much shorter and ask you more for a recognition or understanding of the parts of the equation. There are three different types of problems that you'll see as we go through this. We'll have population growth. So again, the idea of like moose in a national park or rabbits in an enclosure or even people. Spreading of a disease. So here's our COVID virus going on, or the spreading of a rumor. Those are the types of problems that you'll see the most often. Now I have a PowerPoint. I just wanted to show you a question. So this was our moose question. We just did that one. This was a question that I saw on a particular year, and it was mainly wanted to know which one is logistic growth. So you're not being asked to actually do a lot of work here. It's truly just the recognition. So my variable is y. So y is what's changing over time. So you see that dy dt. In order to be logistic growth, you need to have a y and then another factor that has a subtraction with y. This doesn't have enough. This letter A is a. I want to write on this. Hold on. I feel like I can do more if I can write. A is just your basic exponential growth. Actually, A isn't much of anything. B is your basic exponential growth. C has everything in terms of time. You want your derivative to be in terms of your population. D has your population here, which is great, but then we should have the y value here as well. The only one that has a factor of y and then another factor of y is E. So E is an example of your logistic growth model. Okay. That gives you the basics of logistic growth. I'm going to make a separate video that goes through and does some examples with those formulas that I just showed you that go through and talk about a rumor spreading or a disease spreading or even a population spreading and answer some more questions.